So does anyone want to say something or ask a question on the course or something in general? Okay, no one. Okay, I hope I'm recording. I see a small cloud with some flashes. I simply don't remember the Corona time so well. You think I am? Okay. So just one announcement. I know that you are facing difficult times. So the Dean decided the last week of the semester will be devoted only for a recap on things that you have already studied. And this means that actually the new material that we will have is either today and in next lesson. So today we're going to focus on a beautiful chapter, chapter 10, which is very important. In some case, in some sense, we are now facing the really new material in the course. So let us start, unless again, if someone wants to say something, you are welcome right now. Okay, so no comments. So what we are going to discuss at the beginning is, again, this is following chapter 10. We are going to discuss at the beginning the vector potential and the scalar potential, A and V. Now, of course, you have already discussed this and we talked about it a lot. The new thing here is that now we are dealing with the vector potential A, R, and T, and in principle, V, R, and T. And these, of course, give you the electromagnetic fields, E and B. So the new thing here is the time. So up till now, we were talking mostly about static things. And then the first question that we have, which is a rather simple question, is how do we formulate the theory with these generalized vector potentials that are time dependent now. This all comes, of course, from Maxwell's equations. So let us start with just remembering what are Maxwell's equations, and I'll number them. So this one I call G. This is G is for Gauss, which is actually Coulomb's law. We discussed it a lot. I'm not going to elaborate. The second one is, I call it F for Faraday. The rotor of E is B, the time derivative of B, the change of the magnetic flux give you the electric field. I'll call this one N because it says that there are no magnetic monopoles. And the last one is, of course, the Ampere law, which was corrected by Maxwell, minus U0 epsilon 0 dE dt. Okay, Maxwell is, all the set of equations are called Maxwell, but the last one I'm going to call Ampere's law. And what can we say about the vector potential? So previously, we had, let's say with statics, we had rotary equals 0. This is statics. And this is because dB over dt is 0, this term here. So in this case, we could easily formulate a potential V. And we could ask what is the equations for V. We could solve for V instead of solving for E. But you now see that we have a problem because rotor of E is not equal 0 in general because of the Faraday law. And then we need to think about what exactly are we going to do. Before looking at E, which is the more complicated stuff, we immediately know what about A? I think it's very easy. And the equation that is important for the definition of the vector potential A is, of course, N. That is, there is no there is no monopoles. And then immediately we know that some rotor of some function A is equal B. So with respect to B, everything is simple, and it's very similar to what we had before, because there are no monopoles, a rotor of A we had up to now is that this function A now depends on time. We have electric fields, and that means with respect to the potential and the relation.
אלי, אנחנו לא שומעים. מישהו שומע את אלי?
לא. אני גם.
That was I don't know what happened. Let me share the screen again. Okay, so I guess you're back with me. 1 second. We all love this, of course. Okay, so we want to formulate the connection of the electric field now with two potentials. One is the scalar potential V, and the other one is the vector potential A. So we are going to use the Faraday's law because of the following. I can include in Faraday's law the definition of the magnetic field together with A, and then I'll have the following. I'll have rotor. Sorry, what's going on? My iPad got stuck. One minute. Very expensive iPad that should work. I never failed before. Okay. Okay, guys, there is a problem for clear. What's the problem? Anyone has any idea what to do?
מה לא עובד? אתה לא מצליח...
לא מצליח לכתוב. לא יודע למה. מוזר, כי זה באמצע הכתיבה.
יכול להיות שנגמר לעט שלך סוללה או משהו, שהוא לא מזהה אותו? כי זה
אין
כתוב שזה
סיכוי.
לא יתחבר ל...
אני בדקתי את זה, לא. זה לא קשור לעט, כמעט בטוח.
אולי בפתק חדש?
זהו, אני לא מצליח לעלות חדש, זה עוד יותר מוזר. אז אני הולך פה, אני צריך ללחוץ פה למעלה בצד שמאל בכחול. ניו. ואז הוא הולך לזה. כאילו טוב, בוא נעשה הפסקה רגע ואני אנסה להתקשר לאורן שאולי...
למעלה מסומן לך הכלי של האצבע.
רגע, רק שנייה. כן.
למעלה מסומן לך הכלי של האצבע, ולכן העט הוא מתייחס אליו כמו אל אצבע. אתה צריך לסמן על העט למעלה. יש לך את השורת כלים, נכון? יש לך שם עט, עיפרון, מרקר, מחק.
כן.
אז זה מסומן לך על האצבע. אתה צריך להעביר את זה לעט, להכי שמאלי.
אני לוחץ
פשוט
על
ללחוץ
זה,
על העט שנמצא הכי משמאל.
אני לוחץ וזה לא עובר.
אה,
יש באפל ובאייפד כאילו עוד אפליקציה טבעית כזאת של המערכת הפעלה של ה-iOS ולא נוטביליטי, היא פחות טובה אבל אולי זה יעבוד.
אני צריך להבין למה לא מצליח להעביר. כן, אני רואה שאני על היד הזאת. רגע, רק שנייה. אני עושה done. אז אני לא מצליח להעביר את זה עם העט. כאילו שהעט... רגע. לא. צריך לשאול את צ'אט. תצאו ל10 דקות הפסקה, תחזרו עוד 10 דקות פשוט.
טוב.
לא, לא שלוש. תינוק למנה, ביצה.
מורן, בוקר טוב. מצטער שאני מעיר אותך, אבל יש לי בעיה, אני באמצע שיעור. התחלתי את השיעור, הכל היה בסדר גמור. עכשיו אחרי 40 דקות, פתאום העט שלי מפסיקה לכתוב. עכשיו, מה שקורה, אני משתמש בנוטביליטי, ואני נמצא עם משהו שנראה כמו יד. ואני מנסה לחזור חזרה למוד של במקום יד, שיהיה לי עט. אבל זה תקוע על היד. אתה יודע על מה אני מדבר? איזה יד אני מדבר? נכון, נכון, נכון. אז הסרגל כלים תקוע על היד, וכשאני לוחץ על המברשת או על העט או על המחק, הוא פשוט לא מגיב. אני יודע לסגור מה זה לגמרי, זה גם מה שהאייפד אמר. אוקיי, אני סגרתי את זה עם close, זה מספיק או... מלמטה? זה לא עובד לי כל כך. מה זאת אומרת? יש לי את הנוטס הספציפי. כן, אבל אני עושה את זה, אבל יש לי... אני מעלה פשוט את הדפים. אוקיי, כן, עשיתי את זה, הבנתי אותך. כן, כמו בטלפון. אוקיי, זה... לחיצה ארוכה על הנוטבילי, והכל כזה עושה וויגלינג כזה, ולזרוק אותו כלפי מעלה. אוקיי, עכשיו הכל כזה רוטט לי כמו שיכור. לפתוח אותו? עכשיו הוא חזר למעלה בתור אייקון, אבל הוא רועד, הוא רוטט. כולם רוטטים. לא, את זה עשיתי כבר, עכשיו אני מדבר על האייקון, אחרי שהוא נסגר. אז הגעתי, מה לעשות, אני... לא יודע למה, אבל כל האייקונים שלי רוטטים.
ננסה ללחוץ על הדן בפינה הימנית למעלה.
הנה, עכשיו הכל נרגע. נפתח. לא, זה על היד עוד פעם. אני סגר. אני עושה את זה, ואז הוא הולך כאילו לאייקון. הוא הולך כאילו לאייקון. כאילו הוא נבלע באייקון שלו, הוא כאילו נעלם. למשוך אותו מלמטה, אתה מתכוון. עכשיו הוא פשוט נהפך למסך קטן. זה משהו סטנדרטי, אולי זה צריך להיות ימינה ולא למעלה. זה צריך להיות אלמנטרי. אוקיי, עכשיו הוא נעלם לי, אני לא יודע איפה הוא. הוא לא שואל אותי שום דבר. אני מתחיל כאילו, ממש מלמטה. נו, כן. בינתיים הוא המסך קטן. הוא קטן קטן קטן, אבל רק הוא קטן. ואז הוא קופץ לי לצד. לא, פה באמצע, אני הייתי באמצע השיעור ופתאום הוא נתקע לי. הכל כתבתי, הכל היה בסדר, ופתאום היד הזאת קפצה. טוב, בסדר. אז אני אנסה את זה. רק שנייה. יש את ה... כנראה שלא, יש פה שתיים שהם יש פה שתיים שהם הווליום ואחד שהוא חשבתי שמכבים איתו. איך מכבים? יש שיטה פשוטה בדרך המסך עצמו. כפתור נעילה. מה זה כפתור נעילה? למעלה, לא יודע מה זה למעלה, זה תלוי באיזה כיוון אתה מסתכל. למעלה מצד ימין יש כפתור, כן. לוחץ עליו ארוך. שניהם אני לוחץ, זה לא ידעתי. slide to power off, אוקיי, שניהם ביחד, עשיתי את זה. אני לא משתמש באייפד הזה אף פעם.
אולי זה אין לך גרסת פרימיום על האייפד הזה, ובגלל זה יש לך הגבלה על כמות הדברים שאתה יכול לכתוב בכל פתק?
לא, לא נראה לי.
לא סביר.
אתמול כתבתי, אז לא, זה לא זה. אוקיי, בואו ננסה עוד פעם. לכבות ולהדליק, השיטה הכי טובה. אוקיי, בואו נראה, נוטבילי. אני עדיין תקוע על היד הזאת. כן, אני לא יכול גם לעשות פתק חדש. לא יכול. אני חושב שאני אנסה לעבוד על יש פה איזה משהו אחר. start writing, יש pages. אבל גם pages לא עובד לי. לא יודע אם יש לי notes.
אלי, אם אתה משתמש בעט סתם כדי ללחוץ על אפליקציה כלשהי באייפד, זה עובד? כאילו, לראות אם סתם העט מחובר בכלל לאייפד.
נראה לי שלא.
אם זה אפילו לא פותח אפליקציה, זה אומר שהבעיה היא בחיבור. ואז או שזה בהגדרות, כנראה שזה בהגדרות, כי סוללה באמת יש.
יש סוללה, ופתאום באמצע השיעור העט הפסיקה לעבוד. אני לא מבין את ההיגיון של הדבר הזה. לא, לא נגמר לו, אני בדקתי את זה טוב טוב, יש סוללה. אפל פנסל 89%. זה לא הסוללה.
בהגדרות שלך יש אפל פנסיל. הגדרות של האפל פנסיל. יכול להיות ששם משהו כבוי אולי?
אפל פנסל. אבל זה היה באמצע השיעור, אז זה קצת קשה להאמין. הנה, העט שלי תאונה, זה בטוח. ההגדרות, בוא נראה איפה בהגדרות. איפה ההגדרות שלי? הנה, בסטינג אתה מתכוון.
כן.
פנסל, אפל פנסל. אז באפל פנסל, only draw with Apple pencil, scribble, try scribble, try writing a few words. הוא מצליח לכתוב על היי אורן. בקיצור, הציעו לי ללכת לסטינג, ובסטינג אני יכול לעשות try scribble, ופה העט עובדת. אני יכול לצייר משהו למרות שזה, כן, למרות שזה, אני כותב ואז הוא מוחק את זה אוטומטית. אבל לפחות הוא מגיב. וזה only draw in Apple pencil ולא יודע. בוא נחזור. אבל זה כאילו שהעט לא עובדת, אבל יש כל ההרשאות קיימות.
הבנתי, אני אסתכל רגע בצ'אט מה זה יכול להיות.
זה פשוט התקיעה של היד הזאת. שאלתי את צ'אט ומה שהוא אומר לי, לפני שנתקשרתי לאורן, הוא אומר לי בדיוק את הדברים האלה, לכבות, להדליק, לנתק את האייפד מהמחשב. כל הדברים האלה עשיתי, אבל הוא עדיין תקוע. הוא אמר לי להשתמש ביד במקום בעט כדי להזיז את האייקונים על ה-notability, אז כל הדברים האלה לא עזרו. כאילו, הוא פשוט תקוע על היד, והוא לא נותן לי לעבוד, אבל הוא גם לא עובד על הנוטס. בואו נראה על הנוטס. בסדר, אין לי ברירה. בנוט שלי כתוב drawing not supported.
הבלוטוס שלך פאול, דולק?
הבלוטוס על מה?
הבלוטוס.
יש לי מחובר דרך המחשב. אני חושב שהוא, כאילו מה שאני עושה, אני מחבר את האייפד למחשב, וזה הכל בסדר, זה משודר.
לא, אבל הבלוטוס באייפד מחובר כי העט מבוסס על החיבור בין הבלוטוס לאייפד. אולי
אוקיי,
בטעות חיבית את הבלוטוס של האייפד.
אוקיי, אז מה אני הולך לסטינג שוב, נכון?
כן, בפינה השמאל עליונה תפתח איפה שיש לך את האייקון של הסוללה והווי-פיי, תבדוק אם הבלוטוס דולק.
Apple Pencil connected. כתוב AirPods 2 not connected, לא מבין מה הקשר. Bluetooth on, connected to accessibility you can. נעלה את זה על המסך שכולנו רוצים. רגע, רק שנייה. זה הבלוטוס. אתה רואה את זה?
כן, זה נראה שהוא עובד. אז זה כנראה לא הבעיה.
הלכתי
הנה.
לפנסל, אני עושה try scribble. הנה, אני יכול עכשיו אני לא יכול. אני יכול לסרטט פה, אתה רואה? אני חושב שאתה
כן,
רואה.
כן. כן, כן, הוא מחובר.
ואז כשאני עובר לנוטבילי, אתה רואה פה למעלה בצד ימין את היד, אני מנסה להזיז את זה. אני יכול להזיז את האיקונים, אבל לא יכול ללחוץ ולא יכול לבחור משהו.
כן.
וזהו, זה מה שאני יכול להגיד. זה מוזר. אני לוחץ על ניו, אני לא יכול. ניו מביא אותי טוב. אורן, בקומה של... אתה איתי? אני אעשה את זה עכשיו. אבל שוב, אני מצליח לכתוב עם העט בסקריבל הזה. סגרתי אותה. ברור שלא סגרתי אותה. מישהו בבית יודע בדיוק איך אני סוגר את זה הרמטית, את הנוטבילי הזה? הם כבר לא נמצאים.
אתה מתכוון לסגור את האפליקציה, כאילו, שלא תהיה דלוקה גם כאילו, יישומים שפתוחים?
עד כמה שאני מבין, אני פשוט צריך ללחוץ את זה למעלה, להעיף את זה למעלה, וזה עף, זה סגירה, אבל אולי יש סגירה יותר הרמטית.
לא, אני מכיר שברגע שאתה מעיף את זה למעלה, אז נסגר, כאילו. חוץ מלמחוק, אין משהו יותר הרמטי.
זה לא פתוח החדר?
ועכשיו למשוך את נוטביליטי למעלה.
עכשיו. עדיין תקוע. תקוע וגם אני לא יכול לעשות ניו, זה משהו פה לא בסדר. כשאני לוחץ על הניו, אז הוא אומר לי unlock, unleash the power of notability, unlock. אחרי זה הוא אומר
הוא
לי
רוצה
אוקיי,
שתקנה איך קוראים לזה? סאבסקריפשן. זאת אומרת, הוא
אחרי
טוען
שאני אקנה את הסאבסקריפשן,
גרסה מוגבלת.
אני לא יודע, זה מוזר לי מאוד. חשבתי שזה סאבסקריפשן, למה אני צריך לקנות עכשיו חדש פתאום באמצע...
יש לך כבר סאבסקריפשן?
היה לי מזמן, אני לא עדכנתי אותו אולי, אבל...
אז אולי בגלל שהוא לא מעודכן או משהו.
אולי, אני לא יודע, אבל אתמול הוא עבד מצוין, אז זה מאוד מוזר. טוב, אני אנסה למצוא משהו אחר, אני ארד לקומה 3. אורן, קומה 3, אתה אומר סגור, אבל איך אני אכנס? התא של המזכירות זה יחד עם כל התאים האחרים? ואז אני צריך, כאילו אני צריך לקחת את הזום, אני צריך לפתוח זום חדש שם או... כן, אוקיי, ואז אני צריך לשלוח לכולם את הזום אוי אוי. אז מה שמוזר, איך זה, גם בנוטס אין לי הרשאה בכלל לעבוד עם העט הזאת. רגע, הנה נוטס, רגע. זה מוזר. אוקיי, יש לי אפשרות לעבוד עם נוטס, בואו ננסה להסתכל על זה רגע. וקורה פה משהו סופר מוזר. אני כותב עם העט, הוא כותב משהו, ואז הוא מתרגם את זה לאיזה אות. אתה מכיר כזה דבר? אני כותב עם העט בנוטס, מצייר משהו, ואז הוא הופך את זה לאותיות. אתה רוצה אולי לעלות לזום, אתה תראה מה קורה, הסטודנטים יכולים לראות את הנס הזה. זה קשור למקלדת. כרגע אני לא רואה שום סרגל כלים. יש לי אייקון של זבל, של... איך אני מעלה את הסרגל כלים פה? למטה יש לי, סליחה. מה זה? למען האמת אני לא רואה את... פנסיל, יש לי פנסיל סטינגס. לא רואה את, יש לי מייקרופון, יש לי כל מיני דברים כאלה. העט זה לא ככה אצלי, יש פה איזה חיצים עגולים כאלה. זה כאילו הכיוון כתיבה. לא מבין את זה. טוב, אני מנסה. טוב, בסדר, תודה. אוקיי, אני אנסה לעבור למחשב אחר למטה בקומה 3, אבל נתחיל אולי ב10, אם אנחנו נהיה אופטימיים. אני מצטער על התקלה הזאת.
להתחבר ב10?
תתפללו, אבל אני פסימי.
טוב.
להתראות. אוקיי. עכשיו אני עושה share. Advanced iPhone via cable. share. Hello. אוקיי, רגע יוסי. בוא נראה אם יש סטודנטים בכיתה. שלום, אתם שומעים אותי?
שלום, שלום.
שומעים.
אוקיי.
שלום.
כל הכבוד לכם, איזה עמידות של העורף. יפה מאוד. חשבתי שכבר כולם ילכו. נראה לי שאני אסתדר, יוסי, תודה רבה. אני הקלטתי כבר שעה של ריק, והוא יזרוק אותי ב-12, אבל טוב, נראה כבר מה לעשות. תודה, ביי. אוקיי, רק שנייה. אוקיי, אתם איתי? Yes, okay. So, okay. We will start from the beginning. I mean, because I don't have the notes, but I'll repeat what I have to say, and then hopefully I'll do it a bit faster than what I did before. So we start with Maxwell's equation. This one I called Gauss. Div B equals 0. I called no charge. Then I said we have Faraday's law minus dB dt. This we called Faraday's law. And then we had Ampere's law, rotor B U0 J minus U0 epsilon 0 d dt. This is Maxwell's correction. And this one I called Ampere. Then our goal is to find the, first of all, to clarify whether or not we can use the vector potential. And immediately from equation no, we immediately understand that B is equal rotor A. And the idea now is that A is a function of both space and time. So previously in statics, it was a function of R only, and now it's a function of T, but otherwise the structure of the theory is precisely the same. We now use the Faraday's law, and we just plug in this definition of the B. This is d dt, and then we have here rotor A. So what we can say is that the rotor, I just change I bring this A to the other side of the equation. This minus will turn into a plus. So the rotor of E plus an object called dA dt, again, where did the derivative with respect to time come? It came from Faraday's law. This is obvious. This is equal 0. And this is a good thing because then you see this object here. We can immediately say that there is a potential V that will be useful. And this implies that the following, that E, let's write it down a bit slower now because this is the new part, is equal to some function V, R, and T, which is the potential. And again, the new thing here is the time. So what we see here is that the electromagnetic field is simply, this is, here we have div, of course, and the minus sign. So again, the idea is that with this div, the rotor of a div is equal 0. So all this junk, I can write as div some function V with a minus sign. This is just what we're used to. And then what we see is that E, and this is the important equation, is equal to as usual, minus div v minus dA dt. So the message here is very simple. When we want to calculate B, the magnetic field, and E, the electric field, we, as usual, need to calculate two functions. One of them is a vector A, another one is a scalar V. But when we calculate the electric field, we need to take into consideration the time dependence of A. This is the new term here that we have, and this means that usually you are used to the fact that in order to calculate the electric field, it's enough to calculate the potential. Well, this is not true anymore. Now we need to calculate both in order to get the electric field, while B remains perfectly as usual. Okay, this is all great, but so far we did not use all the equations. Let us continue and try to simplify. So what I'm trying to do now is, instead of vectors E, B, and A, and then V, I want to work only with the potentials and get some equation for the potentials without invoking the fields. And of course, I did not use all of Maxwell's equations, so something is clearly missing here. So to continue, let us look at Gauss' law. dV is rho divided by epsilon 0. But we now can, instead of E, we can use the potentials, and let us do that. And then we'll get something which will be familiar to you, but with a new twist. So here I have div V plus dA dt. So this is just the electric field now. This is equal to the source of the charges that we have in the system. And of course, what do you see here? You see immediately, you see a Laplace-like equation. I just change things around. This minus will go to the other side. And then I'll have the Laplacian of V plus, because again, d dt div A is equal to minus rho epsilon 0. Now, what we did before, if you remember, was we used we used Coulomb-Gauge, where this div A was vanishing, but now we are going to use a different Gauss soon, and the new Gauss is called Lorentz. There is no T. This Lorentz is actually a Danish physicist. So there is Lorentz. This is from the famous transformations. And this is just another guy. And everyone gets confused between these two people. So, you know, I'm just pointing out some injustice for history. Everyone say this is the famous Lorentz, but it's actually the second Lorentz. Okay, so we have an equation which looks a little bit like a Laplace-like equation, but of course with E, but we still didn't use the Ampere law. So let us use the Ampere law and see what we can change in this equation. So the Ampere law, we already stated what it is. It's this equation, U0 plus J as usual, with the plus sign now, U0 epsilon 0. And here we have dE dt. So what I'm doing now is actually, you see in this equation, you have this, the derivative with respect to time and the derivatives with respect to space look differently. One of them comes with the Laplacian, the other one is actually mixed because you have both time derivative and space derivatives together. What we are trying to do is to tidy things up, and thinking about relativity, we know that in some sense the position and the time should be on the same footing. So we are trying to arrive at equations where space and time are not exactly the same. Of course, they are never exactly the same because time always flows forward, but that they are treated in the same way. And this is what I'm trying to do now by some massaging of the equations. So I can write this equation, this Ampere equation, with the vector potential. So here I just change the B with the rotor. This is, as usual, I'm just copying now plus u0. Okay, so now, sorry, now I'm going to use the fact that, so here I use the B, and now I can use the definition of the E, which is up here in this equation. So I'll get here a minus sign, u0, e0, and then I get the following. I get div ddt v minus u0 epsilon 0 second derivative of a ddt. Where does the second derivative come? It came from this derivative with respect to time. That is Maxwell's correction to Ampere's law, together with this definition of the a dt. So two times the derivative gave me the second derivative with respect to time. And this is something that I like, because first of all, I see in this equation, I have the Laplacian, and here we have the second derivative. And also we like the second derivative because we remember that in the wave equation, we have second derivative with respect to time. So you can understand where I'm heading now. Now, I need to get rid of this rotor of rotor, and here I use a simple definition, which is div A minus Laplacian of A. This is an identity, and again, I like this Laplacian. We have a Laplacian with respect to V, and now we have a Laplacian with respect to D. So if we tidy things up, I move the J to the other side of the equation. So it's minus U0J, which is the source term. This is equal to Laplacian of A minus U0 epsilon 0, and the second derivative now of, with respect to time, still of A, minus this derivative that comes, for example, from here, which is the following, div A plus U0 epsilon 0 dA dt. Now, this guy is simply ugly. The first part is beautiful because we see that time and space are treated in the same way. Now, the idea of the Lorentz goes, okay, Lorentz. I'm not proving it, is that we can take this ugly term and make it into zero.
Isn't it supposed to be V and not A in the end there?
Yeah, here, sorry, here it's V. Sorry, yes. Thank you. Of course. So we are, the claim of Lorentz is simple, that we can simply take this ugly term and make it into zero. I'll soon explain why, but if this is true, we can conclude the following. So let us write it down. This is this gauge. And if this is true, we can write the equations with something called D'Alembertian. So we usually have something called Laplacian, and a D'Alembertian is the same as a Laplacian, but with an additional term. So it's an operator. So of course the Laplacian in Cartesian coordinates is simply the derivative, the second derivative x, y, and z. And now we add the second derivative with respect to time. This is a generalization of the Laplacian. And then you see this in this equation, for example, and you can write then the equations like this. So these are the basic equations. If you want, minus U0 times J. And similarly, I'm not showing this, you can write V equals minus rho over epsilon 0. So in principle, these are the equations that you need to solve. What we are going to do is actually we are going to solve these equations, find What do I mean by solve this equation? It will be a formal solution. It will be a formal solution in the sense of I'll give you some j, and with some integral, I'm going to find a, and give me some density of charges. With some integral, I'm going to find v. And that is essentially replacement of Coulomb's and Biot-Savat's law for the solution of Maxwell equation. So again, the main goal is to find a rho given some general j and rho. Sorry, find.
It's A and V.
Yes, a and v given some j and rho. This is the usual thing that we always do when we solve when we solved already electrostatics, but now we are doing it for the Maxwell equations. And up till now, the only thing that was different was that we redefined the Laplacian. You see, this is similar. Let's say this equation is similar to the Laplace equation, but now with an additional term here with respect to time. Let me just briefly comment on the meaning of the Lorentz gauge. I did not explain why I can choose this, but I'll just remind very briefly how this comes out. So the idea of gauges, as before, we had this already in the class. I can always change from one gauge to the other. And I do it in the following way. And this is a claim. If I have some A, I can define a new A prime. And this A prime is defined up to this scalar function lambda. And I have to take this div of the scalar function. And the meaning of the gauge transformation is simple. E, B are the same. What do I mean the same? If you choose A tag or A, or if you choose V tag or V, the answers are the same. And this gives you flexibility in the choice of these potentials. Again, this is not new. We know this. We know this for example, we know it in high school from the fact that the potential is defined up to a constant. So here it's not up to a constant, but it is up to a function, lambda. And it's not exactly up to this function, lambda, but rather you see again the symmetry between space and time. For the A, we need to add the div of lambda, and for the V, we need to subtract minus. We had this minus also here, if you noticed. We need to subtract the minus of the time derivative of lambda. So lambda is a function of space and time, and it's an arbitrary function. There are many, many functions like this that we can do this trick. And one of these choices leaves you to Lorentz gauge. There are many other choices, but this choice, the particular Lorentz gauge, is very useful because the equations at the end are very elegant, and we got rid of what I called before the ugly equations. So why are these two gauge, two fields? Why is, for example, A prime and A the same? From point of view of physics, they are not identical from a point of view of mathematics. They are two different functions. And this is very easy to see because all I need to do is I need to take the rotor of A prime is equal to the rotor of A plus rotor of div lambda. But this guy, as you know, is equal 0. So this is equal B, the real physical magnetic field, whatever the choice is of A tag or A. It doesn't matter which one you choose. You can always add this function, which is div lambda. And similarly, I can show for E. So let us look at E prime. Then I need to use the definition that we had before. That means the trick here is I need to take the div of V, but I also need to take the time derivative of A. So this is equal div V minus d lambda dt minus d dt A plus div lambda, right? I'm just plugging in the definitions. Here you see the definition of A prime, and this is the definition of V prime that we had above. And this is just the definition of E in the tag reference frame, in the tag gauge. So, okay, but now what you see immediately is that this term and this term vanish, because we have div and then the time derivative, and here we have the time derivative, and d minus minus gives you plus, and then they simply vanish. This is the reason why here, in one case, we add the div, and the other one, we add the time derivative, and now you see that this particular choice, when you take the div of v, you get div d lambda dt, and when you take the time derivative, you get the same, and that's why you have a plus and a minus here, and that means that E prime is equal minus dv minus d dt A, but that is by definition the field in the original gauge, and this is the real physical gauge. So you can use, so the E prime and the B prime are equal to the true, whatever that means, magnetic fields. I think this is clear because it's also similar to what we had before. We can ask the following question: what is the lambda that can be used to satisfy the specific Lorentz gauge? I'm not going to do this, but one can easily show by inserting that the following equation for lambda. So this is this equation, and due to time, I'll skip a bit. It's very easy to prove. So this is an equation for lambda, and what you see here is again the Lambertian, and then this is equal to some function r and t. And if you want to know what is this function r and t, well, it's easy to show that this function is simply given by div a, the minus plus, sorry, u0 epsilon 0 dvdt. So again, the A is with the div, and the potential is with the V. So what am I saying here? Let us assume there is a solution of the Maxwell equation. Then there is some A and there is some V that solves this equation that we had before. And then this solution, whatever it is, whatever gauge you want to choose, and it's totally arbitrary, what is the gauge, gives you this function f. And then given this function f, which depends what is your original A and what is your original V, you have an equation for lambda. Now, this equation you can solve in principle, and then there is such a lambda. Now, this is not so interesting from practical point of view in the following sense. All you need to know that there is some lambda that satisfies this equation, and then you can always go from one gauge to another. But of course, what we do is we work in this Lorentz gauge, and this is under this special type of gauge, but simply again because of the symmetry. Okay, so now our opening session has ended. Now we need to solve these equations. If you have questions, please ask them now. Okay, so we want to solve these equations, and to do that, we are going to use the same notation that we had all along the course. So let us remind ourselves, we have some body. This is a physical body in which we have some currents, and in each we have some charge density. So J and rho are defined here inside. In this element, which is a physical element, we have some delta tau. Again, this is the same as what we had, and we will later need to integrate over over this volume, whatever it is. Of course, this volume can be composed of many different volumes of wires and whatever you want, but this is the basic definition of the system, I would say, that gives you the charges and the currents. The charges and the currents, as usual, will depend on space and in principle on time. So at this point in space, this small box, you have some current and some density, and similarly in other points in space. And then the question here eventually is, what is A and what is V? Given these configuration, we assume that it is given. Now, from A and V, what do I get? I get E and B. Now, one of the students complained that I don't provide everything given in Mr. Griffith's book. So what I'm going to focus mainly is on this, and then taking the time derivatives or taking the divergence of V, etc., taking derivatives of this, you get E and B. So some of my derivations do not include these steps. But so if you want to fill in the steps, go to chapter 10 in Griffiths. But my point is very simple, that I'm giving you the essence of Griffiths, not all of it, but I'm teaching all of Griffiths. Again, some people complained about this, and it was not so clear to me what is the complaint. Okay, let us continue. So I have this system, and then I need to define, as usual, some observer and some point in space. So I have here the reference frame, which ideally we'll use symmetry to choose it, but now I just choose it kind of very generally. And then we have, maybe this is not a good way, this is vector R. So R is the location of the observer, and what we would like to know is the vector potential A and the potential V at this point P. As usual, we connect this is the reference frame. We have this delta T here inside, and then we connect this point like this. This is, of course, R prime. And we need to, eventually, we need to look at many R primes. So R prime will be an integration variable. And this is, again, exactly like we had before all over the course. Actually, this is the reason why I taught you the course so slowly, is that you'll understand these notations. I think by now you understand them perfectly well. And you know also that what is going to be important is this vector that describes the distance between the charge and the point of observation, which I denote by R minus R prime. So these are just definitions and nothing new here. Now let us give the solution and we will discuss it. This is the main equations if you want. They are formal equations, of course. So what would you say is the solution of this the Lambertian? In structure, it looks very similar to what you had up till now, but there is a huge, huge difference. Of course, it's very different, but now I'm going to write it down and it's very similar. Maybe it's not so surprising that it's similar, because what did we do? We just changed, let's say, a Laplacian with the Lambertian. Okay, let us see what is the solution. So I'm going to write it down and we will discuss this. And in the homework and further reading, you will try to understand this beautiful and very central equation. So this integration is over the volume, over d tau. I need to add up all the elements. And then I'm going to write rho R prime T divided by R minus R prime. And that's it. Well, not really, I'm cheating a bit. So what do we see here? Well, 1 over 4 pi epsilon 0, that's the famous Coulomb law. You call it K in high school. What is 1 over R minus R prime? That is also Coulomb's law. The potential goes like 1 over the distance. What do we have up here? We have the charge density. So what is new here? The new element here is that this guy is going to call TR. TR is called the retarded time. It's not the usual time. In these problems, we have two types of times. One of them is the laboratory time, that is just the time that you are in. And the other one is this retarded time. The word retarded means backward time. I won't say what you say on stupid people, they are retarded people. Okay, so what is this retarded time? This is the main issue, I'll soon discuss it. What is this A? It's again very similar to the usual equation. This is the beauty of the Lorentz gauge. We have the volume, we have integration d tau. What will appear here? The J, of course, because we know that currents give you magnetic fields. Here we have R, here I have time, and you can guess already what this means. And then you have R minus R prime. 1 over r minus r prime is again not surprising, because again this happens in the Biot-Savart law. For example, in static case where you don't have time t, this is of course new. But again, what is new here is the fact that here we have this r, again, the retarded time. So the whole issue is essentially to understand what is this retarded time. Now, where does it come from? It's the general principle is very simple to understand, but handling this time is not simple at all, in my opinion. It's not simple at all, period. So where does it come from? It comes from a very simple effect that you can immediately realize. Let's say you have a system here and you have some j that depends on time t, and then you are very far away. When I mean very far away, I mean there is a very long distance between the body and the object, that this point in space where you're looking for. For example, let's say this is the star and we are now on Earth. So it's extremely far away. On what scales is it far away? On scales of the time where this current, so that, let's say there is a time t equals 0, and then you turn on the current. Before that, there was no current. Now there is a current. We understand that information will flow, will reach the observer here only after, let's put it differently, not before. Excuse me? Let's write it like this, not faster than speed of light permits. And this means that what you care at some time t is not what happens in the system at time t, but what happens in the past. This is a kind of very intuitive thing. For example, if you look in the sky, you look at the evolution and you want to look at the Big Bang, for example, what you need to look at is at very distant galaxies and stars, because they emitted light long time ago and it took them a long time to reach us. So when we look at them now at time t in our laboratory frame, we are actually getting information about the past, simply because information kind of moves in a way which is always slower or equal to the speed of light. In our case, it will be in the speed of light. So this is the general idea, but how do we precisely formulate it, and what is this TR? So again, we add this box, and we add this space, and we are at a distance r minus r prime relative to some reference frame. That is this distance. And then I'm going to define now the retarded time like this. This is a definition. It comes out of the equations. I'm not proving this right now. And this is the very important equation because it defines you the retarded time which enters into these equations. So what you need to do when you solve these equations, you first need to find the retarded time. And the retarded time is complicated because it depends both on r and r prime. Of course, it depends on c. C is the speed of light. So you need to find this retarded time. That will be first stage of the solution. Once you have this retarded time for a given time t, so you know what is t, you know what is r, and you know what is r prime. And then you can find tr. And then you need to change, because here you need to change, you integrating over r prime. So then you go to a different r prime. Let's say in this box you add it for one r prime, but now you're looking here, then you have a different r prime. So for each r prime, there is a different tr. So don't confuse this r with this r and this r. Again, this small r is for retarded not for our position in space. This TR depends both on R and on R prime, hence it's complicated. And what does it say? This is the basic physics. It's very simple. The time to reach for information, for example, the switching on of a field or some either density or current, to reach the point of observation, you need to know the distance between the source, which is R minus R prime. You divide by C. And then the relevant, that is the most important word, the relevant information came up in a previous time. TR is positive, but not bigger than TR. So it's important. TR is always less than T, is always bigger than 0. I'll comment on that. And then T minus TR is the time where something was changing in the system, or the relevant time for the density and the J that enters into these equations. So this is the basic equations that are derived from these Maxwell equations. Any questions right here? Before we go into the details, what is TR and how to calculate it, etc.?
T is the time now.
T is the time now. So I have my observer here. He is defined, his position is defined relative to some reference frame. That defines you, the R. And of course, there is a clock. The clock, the usual clock, the clock that is in Schrödinger, Newton, every equation in physics, that is the current time T. Now, in practice, in real problems, what you will find, and soon we'll do that, what is the origin of time? Because we have origin of space. Maybe that's your question, and even if not, I'm going to answer it. So in many of these problems, what we had, the origin of time, let's say at time equals 0, there was no current. Then someone comes and turns on the current. That is time 0. And then I have my laboratory time relative to this origin of time. Is that clear? But in a general problem, you are actually, maybe intentionally and maybe not, you are referring to a problem. Let's say the universe was created 1 billion years ago. I need to, in principle, start this time from the beginning of the universe, right? But don't worry, we don't need to do that because we are physicists. So we always have a practical starting point of the system. For example, the time where we took all the charges and put them together, or the time where we started the current, that will be the origin of time. Okay?
Yes, thank you.
So yeah, it's a subtle point, but the short answer to your question, T is the usual time, but we need to discuss its origin. We need to think about it a little bit. So in principle, luckily, we are done because this gives you the solutions. But of course, this is very formal because what does it mean on E? What does it mean on B? Of course, for that, we have exercises and examples in Griffiths, and I'll discuss some of them. But before that, let us discuss the general issues. First of all, this equation has in principle more than one solution. They have two solutions. You can easily see it because if I take this absolute value, this distance, and square it in order to find the equation, I need to square both terms. And then what is the equation for this TR? It's a quadratic equation that all of you know how to solve, correct? However, it turns out, so this equation has two solutions. And then what will we do with these two solutions? So what happens is the following: we get two times. One of them is called T retarded, and other one is called T advanced. So this is A for advanced. The TA is bigger than T, and it's disqualified. So when you solve these type of equations in, let's say, exercises, you will find two solutions. Then you need to ask yourself, is the time bigger or smaller than time T? And if the answer is yes, we as physicists throw it away. But as mathematicians, there exist solutions not contained in these basic equations. So why do I dare throw away mathematical solutions where we have, instead of TR, we have TA? I think it's pretty obvious because of a basic principle in physics, which is causality, which means that the future doesn't influence the past, as far as we know. Even that is debatable by some physicists, but the mainstream physics agrees that the future is not influencing the present. Here we see the time is different than space, that there are certain solutions with respect to time that we just throw away because we believe that what we have in the past and in the present can influence the present, but not the future. Again, is that clear? Because I don't see your heads. Maybe all of you are sleeping. I don't know. I'm talking to myself a bit. Is it clear?
Yes.
Okay, good. So, of course, you know this, but in the equations, I use the relation between the permittivities of vacuum and the speed of light. So this was used also in order to have the speed of light, which enters, for example, here. And of course, for example, in this equation, you immediately see the following, this equation. If c, the speed of light, goes to infinity, well, what happens? Then if c goes to infinity, tr is equal t, and everything is local. There's no question about this retarded time, because the retarded time is equal t. We can a little bit sharpen this point. What do I mean when c goes to infinity? Actually, when I say c going to infinity, I'm committing a crime because c has units. So it's not so clear. When c goes to infinity, it means that at distances which are defined here in the numerator, r minus r prime, which are not too big compared to t. So if this r minus r prime divided by c, I'm not looking at too far distances, then I can neglect this term on the right-hand side, this term, and then t is equal to r. So it's not that previous studies that you ignore this retarded time are not correct. In most cases, we can think about speed of sound as being so big and the scales of the problem small enough in such a way that we can forget about this retarded time and we can look only at time t. But the interesting problems, including radiation and all kinds of relativistic effects, happen, of course, when this condition is not met. And this is the new part of the what let's say what is interesting for us. So before continuing, let us make this into an example. This example will also is given in Griffiths, and it will also be given in the homework by the teaching assistants. I will not go in all the details, but I just try to give you some better feeling on what is going on in these equations. So I'm now defining a problem, and the simplest problem is, let us define the wire, and in this wire I have a current I of t. This current I of t is related to J. It's related to J in the usual way, that when you have a one-dimensional current, then you need to think about a delta function for J in space. Again, this is exactly the same as before. The simplest current I can imagine maybe, and this is related to what we said before, is the following. It's equal I0 for t greater or equal 0, and it's 0 otherwise. So this I of t is a model, of course. So this is the time. I switch it on at time 0, and then I have a constant current. This is an idealization. In real systems, I can open a current. It will have a transition time. And actually, this transition time can be very important. I'll discuss this briefly later. So this is a sharp switch on of a current. And we should ask ourselves the following question: is all the physics that we are going to get reasonable or not? Because this is, of course, an idealization. but we are now using this as a pedagogical example. Okay, so we are going to define the z direction in this direction. And now let us write the z direction like this. So the current is going like up, I of t at times bigger than 0. So this is z. And now I'm going to say the obvious thing, which type of coordinates should we use? The answer is we should use cylindrical coordinates. So this is going to be the distance s. This is the distance s to some point in space where we are interested to calculate the electric and magnetic field here at this point, at point R. So at point S, sorry. So it should be clear that if I look at this point, or I look at, let's say, this point, it's the same thing. This is the same thing because the current itself is independent of space, right? It is just a function of time. So I'm taking this infinite wire and I'm turning on the current, and the current here or here is exactly the same both before time t equals 0 and after time t 0. So the electric fields here and here are obviously the same. And this means that, for example, A and also B is a function of S and T only. So only this coordinate S. So in cylindrical coordinates, we have Z, phi, and S. And phi is the angular dependence, but here, because of symmetry, there's no angular dependence. This is totally not important. The Z is important, but the S will be in the final solution just because of symmetry and nothing else. This has nothing to do with relativity. It's just common sense. So let us now think about this thing. So let us define it a bit better. So again, this is the Z direction. And I'm at some point. So now I'm going to define, this is the origin. Where do I define the origin? It's not so important. I define some point on the wire. This is my origin, always for origin. This is Z along the wire. So the current is going up here. And I'm interested in this point S. And then the current here, for example, is going to influence, as usual, it will have a contribution to the electric fields and magnetic fields at this point. And now I'm going to use simply Pythagoras. This is Z squared plus S squared. So going back to the basic equation that related between the current and the vector potential A, we get the following. A as a function of S and T is equal U0. I need to integrate over space. I'm skipping here the relation that is, again, standard between J and I. I need to integrate from minus infinity till infinity in principle, but in practice not, over this TR, Z squared plus S squared. And I need to integrate over Z. This is instead of integrating over tau, because it's a one-dimensional problem, I'm integrating over Z. Now, the main issue here is what are the domain of integration? This is the main point. So for any time t less than S divided by C, I'll soon explain it, but I think it's also obvious, information did not reach R. What is R? This is the place where we put our observer. Simply said, let's say this is my S, some distance from the wire. This is the wire, this is the I. Let's say this is CT and this is S. So you see this point will send information to this point. This is the observation. This point will send here information. the information will come first from here and later from other points here and here. I think it's clear that the shortest path is from here. But if S is less than CT, sorry, S is bigger than CT, no information has reached because it did not reach from here, but of course it did not reach from here and here because these points are even further away. So now we want to introduce the following. I have this P, or this is the position of observation. This is the position of my R, where my observer is looking. And I have my current I. I define the reference frame in the easy way just below this point P. But again, there's symmetry here. The first claim, which I think is obvious, there is a Z min and there is a Z max. They are symmetric with respect to this point here. Again, this is S. Such that any element of the wire, let's say here or on the left here, cannot send information in a finite amount of time to this point. What I mean here, I'm looking at this problem for some time t. So this Z min and Z max, they depend on time t. What will happen when time t is bigger and bigger and bigger? I think it's very clear for you. At the beginning, only this guy sends information, then a little bit more and a little bit more information. So when t is very large, Z max and Z min are going to go to plus infinity and minus infinity. But now we have a finite time, and then there is kind of what we call a light cone. What does this light cone mean? That the z's that are relevant for the integration are only those z's in between Z min and Z max. What does it mean? It means that other points along the wire are simply too far in order to transmit information in a finite amount of time t, because the speed of light is c, which is a finite number. So what is this Z max and Z min? So based on physics, it comes also from the math, I think it's intuitive, or you need to think about it. What is this thing? This is CT, and this is CT, this distance, diagonal distance. Why is this CT is obvious, I think. It's simply by definition, what is Z max? Z max is the point in space in Z where beyond this point, no information can travel. So again, if I'm here, it will take, the information will not reach this point. And if this Z max to this point P, the distance is CT, what does it mean? It means the current was switched on and time t equals 0. And exactly this information on the switching on came from here to here exactly on the last time. Now I can easily find Z max because this one is S, and then Z max, for example, is square root of CT minus S squared, right? Because this is the 90-degree angle. I think this is clear, but if not, tell me. Based on this, I understand the following, that the A, which is a function of S and T, is this U0 over 4 pi, as usual, integral. I'll write it like this, from 0 to this Z max. So this is Z max. And now I have I0 divided by Z0 plus S squared square root dz. So this dz is like the integration over tau we had before. What am I missing here? Is anyone there?
Z min.
Z min, but I do this by symmetry. It's the factor 2 here. So I can just add the factor 2, and I need to integrate from 0 to this Z max. You can trust me that this is okay. I think, again, I think it's very clear. What did I use here? I actually kind of avoided the difficult task of finding TR here. Why? Because this TR in this problem is simply equal I0. Because I chose a constant current. If I choose a current that is changing in time, for example, it's switching on adiabatically or not in a sudden way, then it will be much more complicated than this. And then usually what you will have here is some integral that you cannot solve. You cannot solve it analytically in most cases. You can solve it in many cases numerically, which is pretty easy today. And then you can get this solution. So yeah, this is really the simplest pedagogical example where we have this constant here, which is very helpful for us. Now, just to summarize, so first of all, do I need to calculate anything beyond this A? The answer is, I don't know, because rho is 0, immediately V is 0. So in this problem, we have only currents and there is no charges. We assume here that the wire is neutral. And then we have only A. Now, usually up till today, and maybe I'm kidding myself, but this is what I believe. If you have A, you believe you have B. You take the rotor of A and you get B. That is absolutely correct. But I showed you previously that with A, you also get the field E, the electric field. Remember how? This is obtained by the time derivative of this function A. So there's no potential there's no scalar potential, but still we have an electric field. Okay, so now we need to solve this equation. And because integrals are not interesting for us anymore, I just write down the solution, which is U0, I0 over 4. No, it's 2 pi. It's 2 pi because 2 over 4 is 2. And here I'm going to write, okay, let's switch to black. Why not? The log of CT plus CT squared minus S squared, all this divided by S. This is correct, but not always correct. This is correct under the conditions of the light cone. And the light cone means that S has to be smaller than ST. So again, this was the light cone. What happens if this is not valid? Then it's very simple. A is equal 0 otherwise. And this means that E and B are equal 0 otherwise. So because I switched on the field, if this condition is not satisfied, which means that we are at large distances, S bigger than CT, the fields are simply 0 because information did not reach and because the current was 0 for times before 0 and because there were no permanent charges, not before and not after time equals 0. Okay? And this is what we expect, actually. This is what we expect from a causality and from a simple aspect of relativity. Now we can find, in principle, we can easily find d dt A. So again, even though the potential V is 0, the electric field is not 0 unless for some reason the time is independent. If A is independent of time, then of course this goes away. And again, taking derivatives is not something I'm going to spend time. But from here, we reach one conclusion immediately without doing the derivative. E is parallel to A, which is parallel to what? To I, which is in the Z direction. And this is, of course, general because you see it from this equation is general in the sense that if the potential V is 0, this is general. Okay, so what is this field? E. This field is given by this equation, minus U0, I0. Of course, this is what we expect. If the current is 0, of course, we have nothing. Here we have C divided by square root CT squared minus S squared in the Z direction, as I already explained. And here S is less than CT, and it's 0 otherwise. Okay, so I'll soon give you B, but what do you think about this E? It's very, very strange because, I mean, what happens up till now, well, maybe it's not very strange, but usually if you have a neutral wire, the field is, what is the electric field? The neutral charge, you are used to think that, you know, E is 0. Of course, this is not the case, but essentially because of Faraday's law. But let us check that we have some common sense in our mind. What is the common sense case? Let's say that S is much, much smaller than CT. Or let's say C in some world is infinite. What will happen? E in this is a case which I call where the position of the observer is relatively close to the charge, relatively close to the wire. Then this E is proportional to, this is not alpha, I'm just deleting everything. You see here CT and S, so I'll get here C divided by CT, Z. I get other things that I don't care about, all kinds of constant. This goes like 1 over T. This is the important thing. And you see this goes to 0 when, not immediately after you turn off on the field, of course, because then this equation is not holding, but in general it goes to 0. So there is no electric field in this limit, but in general there is, of course, otherwise I will not be talking to you. When is the electric field the strongest? Where? In space. You see it also from here. You see that if S is more or less equals CT, then E actually diverges. You see CT squared minus S squared. Let's say they are nearly the same. Of course, S has to be bigger or equal to CT. If S is exactly equal to CT, you diverge. But now you can ask this question, is this divergence, is that physical or not? Anyone want to say, is this physical or not physical? Or can you in principle find it? Maybe you can find an approximation like this, or an electric field equal infinity is nice, no? I mean, we can send we could send such a pulse to Iran by switching on a current here, and then we will kill everyone, right? Because the electric field will be infinity. That will ionize them completely, and that will happen in the speed of light. So, okay, we don't do that. Maybe it's not because we are too humane or something like that. Okay, I got carried away a little bit. But what do you think? Is this physical, this divergence?
No.
Okay, it is not physical. I mean, any infinity in physics is questionable. And especially this one. And I guess you want to say why it is not physical, or what is screwed up here?
This is very similar to the self-energy of the electron.
Okay. So you went backwards in time, and absolutely correct. The self-energy cannot diverge. Okay, let us elaborate on this. You have the point of view of energy, which is excellent. Why does he say this? I'm not sure that he meant it, but what will be the energy of the field? It is proportional to E squared. This is the energy of the field. the energy of the field will behave like CT squared minus S squared. This is not the energy of the field, it is the energy density of the field, right? This is the energy density at a point. At which point? At point S. Sorry. But this energy, can energy density diverge? Let's put another question. Is that against some basic rules? Can an energy density diverge? Do you want to answer? Energy density, okay, you can claim it's not physical that it will diverge, but the integral over the energy density, which is the energy, that cannot diverge unless you have infinite amount of energy to put into your wire. And you can show that the integral over this energy density over space, that gives you infinity. So that would mean if you could create such an electric field that the total energy would be diverging. And when you have divergence, it's a bad signal. So all this divergence, it comes from fast, sudden switching on of I. If you do similar problems where I is smoothly turned on, you will not get this divergence and the physics will be very different close to the light cone. What do I mean here, close to the light cone? Close to the case E equals CT, you'll have a different behavior because you switch it up slowly and then you will not have this divergence. What about B? B, I calculated A, so I can also calculate B by taking the rotor. I'm not doing that. Then B is U0, I0 divided by 2 pi S CT, okay, CT squared minus S squared phi. Phi is the azimuthal angle. I think I wrote it with a different phi before. This is the cylindrical angle. And this is also obvious from the right-hand notation. The current is going in the Z direction with the right-hand notation. The directionality of the current, as usual, is in the direction phi, kind of looping the current. The usual thing. That is the directionality. What is new for us is these the dependence, which is the time dependence. This is again for B as before, inside the light cone, as we had here before. This is B goes to 0, S bigger than CT. So again, there is a divergence like before when CT is approximately S in this problem, and all what I said before is the same. There is a big difference between the two guys. What do we expect in the opposite limit? If S is much, much smaller than CT, so what is this limit? This is the limit where things have kind of settled down. You are not so far away. The initial pulse, you already forgot about it. Then you see, of course, that CT squared minus S squared, this is more or less equal CT squared. And then B is going like U0, I0. I'm just copying from the above equation, 2 pi S. I take the square root of CT, divide by CT, and that's it. So this goes like phi. And this is what is learned in high school, which is of course correct under these conditions. This is what we get from the Biot-Savart's law as usual. Here I think I'm missing a sign. No, I'm not missing a sign, sorry, it's a plus. So unlike the electric field, the magnetic field in the small s limit is finite. But this is, of course, what we expected. There is no relativity. There's no dependence on C, explicit dependence. I mean, this equation is C independent, and you don't need relativity for that. If there's no C in the equation, it means that relativistic effects are negligible or maybe a small correction. Okay, so now we have any questions before I continue? Anyone out there? Okay.
Can you,
Maybe.
sorry, can you explain again about the divergence of the electric field? I'm not sure I understood it.
Well, I said two things. First of all, why there is divergence, just from the equation. You see that if I take S equal CT, let's say CT minus epsilon, then this will be something like 1 over epsilon. And when epsilon goes to 0, it will blow up.
Yes.
This is the mathematical statement. It goes to infinity. So if you plot it, you can easily plot this function, right? 1 over CT squared minus S squared square root. And I plot it as S. This is S. And this is S equals CT. So think about time as some fixed time. Time is 1 hour, whatever it is. S is. So of course you see that this equation at this point, this is the S direction. This function will blow up here, right? Because this goes to 0. That was my first point. It diverges. And this means that the electric field is infinite. It was going to 0 at short distances. This is what I said here. It goes like 1 over time, like what do you expect from a neutral, but at the pulse. So you switched on the field, you switched on the current, and then an electric field is propagating in space. And of course, when I change S here, I mean, I change time, this S moves, right? This is for T1. Then if I go for T2, this will be here. So this pulse is moving, and the size of the electric field is infinity. This is my joke, or not, maybe not funny joke. I'm creating an electric field which goes to infinity, and it's propagating, and it's reaching what I called before the enemy, because no one wants an electric field diverging on his body, because that will mean that all your ions will be ionized. I mean, all your atoms, molecules, etc. Something very bad will happen to you. Okay, that was point 1.
And what is the physical explanation?
The physical question that I posed, I said, is this this is the result of this? And my physical explanation was maybe not complete, but my point is that if my second point was that the total energy diverges, which is even worse, which means you need to put total energy. I think this was clear. You can ask me again maybe later. So my point was that this is not a physical problem, in the sense that the original current, I of t, gives you this solution. And if I replace this problem, I'm not doing it here, by a slow switch on of the field. This is my I.
So because the current doesn't come to existence abruptly, there's no divergence. Right, okay, thank you.
This was my point. And you can solve these type of problems for a given profile of I of t, but then the problem is you go back. I just want to emphasize the difficulties a little bit. You go back, you need to plug it in here, but then this depends on TR and TZ, and then it's very complicated. Then you cannot always solve the integral, but in some cases you can solve the integral with an approximation close to this limit where S is more or less CT. Of course, S is always less than CT. you need to approximate these things, and then this divergence will not appear at the very final end of this pulse. I'm not saying you can switch it on faster and faster, and then you'll have some finite, maybe big even electric field, but you'll never get infinity. Okay?
Yeah, thank you.
I will briefly hint to this. Now, but I'm not solving these type of problems here. I just solved a simple problem. We can now ask, okay, we found V, we found A, and from these, what do I mean by found? If I have rho, I get V. If I have J, I have A. Everything in principle. In practice, again, it's super difficult. And from these, both of them, I can get E and B. I just need to use the rotor. I just need to take the derivatives, both with respect to time, etc. One can do that, but this is so bloody awful that according to Griffiths, it was done something like, if I remember, 1988, which for you is maybe a long time now, but this is really crazy that no one wrote down what is the E and what is the B given J and given rho until a guy called Jeffimenko. Came and did it. Now, why did it take so long for people to write these equations? It's not that Jeffimenko, with all due respect, and I do respect this guy, I think he was some Russian physicist or mathematician. It's very simple. It's not because E and B were not calculated for thousands of examples, but simply people calculate V and they calculate A, and then later they use the derivatives. They don't care in the mathematics to find general expressions for E and B. So Jeffimenko came very late in the history, and his equations are given in Griffiths, but they are so awful equations that I don't want to give them both, but I want to discuss one of them. So Jeffimenko proved the following for E. What do I need eventually for E? I need not only rho, this is just, I'm just telling you now on the tip of the iceberg so I can direct you to the most basic thing. Usually we are used to the fact that the density gives you E. And indeed, the density gives you the potential. I showed you this equation before. We had this. Give me the density, get the potential. Everything is fine. This is this basic equation up here. Give me the potential, get V. But is the potential by itself, sorry, give me the charge density, give me V. But for the electric field, Jeffimenko noticed that this is not the whole story. It's, of course, correct. But to get the electric field, we need both V and the derivative of rho. And this is a point that I want to emphasize. This is the time derivative. The dot of the time derivative of rho is important. Similarly, for B, what we need, again, we had the equation before, to get the vector potential A, what we need is J. That is good enough to get, again, this gives you A, but to get B, what you need is J, and you will not be surprised, J naught. I might soon explain it in more detail if you are interested in the details. And this is related to what was discussed before, that when you have this sudden turn on of the current that we had in the previous problem, this J dot gives you a delta function, but it gives you a delta function only at the beginning, and this creates this problem. So a smooth derivative here eventually will give you a smooth B. And a non-smooth derivative of the pulse function gives you this divergence. This I'm not proving things here. I'm just telling you a little bit about this. And why do we have these additional derivatives entering into the formalism for E and B? You can basically see this from here. So these equations that we had, the basic equations that we have here, they look so similar to the usual equations, but they are absolutely not. For example, let's take the potential. When I take the potential, I take div of this guy. What will happen? The derivative operation, this div, on what will it act? Obviously, in the usual way. It will act on this one, on 1 over r minus r prime. Are you all with me? You understand what I'm talking about? Let's say I want to calculate the E. I'm taking first minus div v.
Yes.
So I'm acting
ברור
on this.
בעצם תלוי.
But, however, and that is the point, there is another dependence on r. And this other dependence comes here because the retarded time, which we defined before, depends on r. Sorry, we defined it before. So when you take the derivatives, you need to take the derivative of 1 over r minus r prime. This is something you did many times before. But then you need to take the derivative here, the spatial derivative, let's call it, with respect to r of this rho. Now, what do you do, or what did Jeffimenko do? Instead of taking the spatial derivative with respect to r, you see, this is time here, tr. What is this rho r prime at time tr? Of course, it's the density at point r prime at time tr, but think about this tr as some general time. So instead of taking the div with respect to r, what do? You take the time derivative, and then you need also the time derivative of tr with respect to r. It's a kind of like a Jacobian. And this gives you the time derivative of rho that enters eventually in these horrible equations of Jeffimenko that you need both rho and rho prime, and similarly for j and j prime. Let me just write down very briefly one of these equations, just that you can see what I'm talking about. B is formally equal 4 pi, and then we have two integrals actually, j r prime. Now I'm not talking about a wire, right? Here I have this tr, this strange backward time, retarded time, r minus r prime squared. And this part of the integral is very standard. I mean, we had it before. This is because I operated on 1 over r minus r prime with the, what did I do where? I just used rotor A equal B. This comes from here. I use the equation that we had before. And then there is an additional term when I take the derivative of TR, again, using the curl, the math is not simple, R prime times TR. Here I have C, R minus R prime. Ooh, sorry about this, multiplied. All this is multiplied by, sorry, vector multiplication because it's for B. R minus R prime, but hat, this is a vector, unit vector in this direction. All this, oh, sorry, this is with respect to time. All this with respect to tau. You don't need to memorize this equation, but you see here that the derivative of the current enters. You see another very important thing, that you see this term is decaying like 1 over r squared. This term is to the power of 1. At large distances, I think you can more or less understand this is the important guy. Do you see this? Because 1 over r squared and 1 over r squared is decaying faster than 1 over r. So this guy is going to be the important term at large distances. It doesn't decay like you have in Biot-Savart. It's a very slow decay. And this actually brings a lot of problem into physics, provided that the current is time dependent and then you have a time derivative. So this is the new term. Again, the proof of this is given in Jeffimenko's work, in Griffith's work. We are not proving this, and I'm even not advocating you to use it. Always use, if you solve problems, always use A, always use V. Like we did in the simple example that we had before, we calculated A and only later we calculated E. Don't go directly to these equations unless you are a bit of a masochist. Okay, this was a comment. I know that you are very tired. I still believe that I should simply go forward for the sake of the beautiful physics that I'm presenting. Unless there are very strong objections, then let me know. You want to, I guess everyone already left or something like that, and they will listen to it later. Okay, so no objections. So now we are going to treat the simplest problem. What is the simplest problem? It's not simple at all. It's complicated. That is the following problem. I have some charge Q. This charge Q is a point charge. I don't have rho, I don't have J. I just have a trajectory of this particle, which is W as a function of T. Some speed. The simplest case may be, let's say, you go at constant speed at time y. So W is not work, it's the position of the charge. Again, the charge is not spatially, it's a point charge. It's not spatially distributed. So the density, what is the density? What is the current? It's a delta function in space and time. There is a current. Why there is a current? Because in principle there is a current, because there is a derivative here, W dot in principle, with respect to time. Dot is always with respect to time, is not equal 0. Right? So both A and V are needed for the calculation. You cannot, it's not like the other problem, because we have here a charge. In the first problem, we had a neutral wire, and then there was no rho. Here, we cannot do that. And we need both, in principle, we need both A and V to calculate what we want to calculate at the end of the day, electric field and magnetic field that is originating from this trajectory. So this particle is moving, it has a charge, and then I have some observer at some point in space, and he or she wants to know, let's say, the potentials and then the electric fields. This is the very basic problem that we are dealing with. So I'm going to present, towards the end, I'm going to present, if you really want, I'll present the mass. Now I'm not presenting the mass, I'm just presenting the solution, because the solution itself and the mass is not totally trivial. It involves some integrations over delta functions. I'm not doing it right away. Maybe I want to do it, actually. I really want to do it because that's the only way to explain things, but for now I'm skipping it just to say what I believe is the main part of the physics. So we have this trajectory of the particle, and we have a reference frame as usual, and we have some R. This is R. So I'm interested, as usual, with the electric field and magnetic field at this point R. Of course, this is a general point. And of course, this reference frame is just an arbitrary reference frame. The particle at time t is, let's say, here. Now I'm at this point. Do I care about the position of the particle? My clock here is time t, as usual. So I'm looking here at time t. Do I care about the position of the particle at this time t here? The answer is no. I do not care about it at all, in some sense. I mean, maybe you do care, but not for the calculations of the electric fields, simply because once the particle is here, it cannot transmit information to this point like this. It's impossible because the speed of light is finite. And then there is a point, this is intuitive, there is a point here along the path that the information, so this is in a history. You were in this point before. Think about your trajectory from, let's say, your seat to the fridge. At some point along your trajectory, the fridge knew that you are coming because you sent a transmission which is equal to CT. It's not immediately because it takes time. So you managed to move a bit, and then you made one small step in the fridge. It's an epsilon step, but there is a delay. So there is a point here where this point is the point, let's call it the points of influence. And this point is some point along the trajectory at some point m, Tm. Now, here I'm changing a bit the notation of Griffiths. Griffiths uses Tm, he calls it Tr. I find it bad notation, but it's okay notation. Always, Griffiths is always a great book. I call it Tm because this time is essentially coming after my integration over all space. This time Tm, in my notation, is independent of R prime. And this one depends on R prime, like before. Why do I call it M? Anyone knows why M? It's related to retarded. It's also a retarded time. Tm is also have to be, of course, less than T because some previous time in your history influenced you at time T. Why is it M? This is only the Hebrew speakers should know. It's from the word mefager. So M is mefager, like retarded. Okay, it's not mass, it's nothing, anything like that. Okay, so I want to first, I'm starting by just saying what is Tm. I think it's more or less obvious based on this diagram. So we have here, this is WTM, some point along your trajectory in your path. I'm not saying how, I'm not telling you how the trajectory is created. You are pulling this particle. I don't care how it is created. Someone is pulling it. It's moving in time and space based on this point. And at time Tm, it's over here. And we have the reference frame, which is somewhere here. And by definition, this is WTM, right? This is just the vector towards this. And then we have another vector to the observer. This is what I called before R. So here is my observer. And then I have the final one. This is this one, which I care only about the distance. By definition, this is R minus WTM. And how do I define this Tm? This is definition of Tm. This is the retarded time, just similar to what we had before. But again, this is already after integration over R prime. So this is the retarded prime. I just write it, and I think it is intuitive. R minus, sorry, This is important equation. WTM, absolute value squared, that's the distance. You just care about the distance, CT minus TM. So what is this TM? I think you see this from this basic equation. This TM is giving you the time where this point W, the information exactly arrived along this path from the starting point to the observable point when the velocity is c. Maybe this is not so clear to you what exactly I mean by this equation, so let me explain better. This equation I said defines Tm. So let us assume that, just for an example, that this is the Wt, this is the general trajectory. Okay, maybe only for t greater than t0, maybe the particle was just sitting before. Okay, this is from now and forever. This is the position of the particle. Sorry, v times t in the y direction. Why did I choose y direction? No reason at all. So this is just a particle going at a constant speed. And you see y, this is y. Y equals vt, like in high school. There's nothing particular about this. What is the Tm? I need to simply, based on the equation, Vtm, absolute value y, equals Ct minus Tm. Now you see, in this problem, I know what is v. V is the speed of the particle, 2 meters per second, whatever it is. It's a number. You see now very clearly, I know what is c, of course. I know what is t. I know where I'm looking. I know everything. The only thing I don't know is Tm. So this is an equation for Tm. Once I know Tm, I can find Wtm. In this case, it will be Vtm y. Okay, so first you find Tm, then you know what is Wtm, which is the position of the particle in this previous time. And this position is influencing our point where we look at space exactly at time t. Notice also that this equation, if I square it, then I have r minus Vtm y dot r minus Vtm y is c squared t minus Tm squared. This is quadratic in Tm. We have terms like Tm squared. We have terms like Tm and constants. You all know how to solve quadratic equations. And you all know that quadratic equations in general have 2 times. If one of them would become complex, it will not be a problem to solve them. But if you solve this, provided, of course, that v is less than c. If v is bigger than c, then you get nonsense. But if v is less than c, you get 2 solutions. One of them is Tm, which is less than t. This one I take. And I get another solution, which I'm going to call Ta. A is not Ahabal. This is advanced, which is bigger than t. And this one, I just ignore. This is the advanced time, as if time is going backwards. Basically, this comes from the fact that the equations are time invariant, but real time is not time invariant. So this is just to clarify a point that I tried to make before. I'm just repeating myself. You have 2 times, but now I'm saying this with an example. I hope I managed to help you understand this small point about T advanced through an example a bit better, even though I didn't solve these simple quadratic equations. Okay, so now we have this Tm, and what would be a guess? Which is wrong? A guess would be, and I'm just going to think about the potential, V. Maybe V is equal to the following simple expression, 4 pi epsilon 0 R minus WTM. This would be a nice equation, and it's not totally wrong, but it is totally wrong mathematically because it doesn't give you all the physics, but maybe in some limits it gives you what you expect. Because this equation is simply the Coulomb's law. What do we have here? We have here some charge. We understand that velocity is influencing. It takes time to propagate. Then we rule out this position here, and it has to propagate in this case. And then you just replace R by R minus the position relative to some reference frame, and you get Coulomb's law relative to the position of the particle, not at time t, that is obvious, but in the retarded time. However, this is wrong. This is part of the solution. The true solution is much more complicated. So I started with something simple in order for you to start thinking about the solution. What is the correct What is the correct solution? It's V, R, and T. Remember, it depends both on time. The time T controls TR, TM, etc. And it depends where you look at in space. We have a similar equation for A0 for capital A, which I'm not writing. This is even given by this lovely, lovely equation, which means that it is pretty overwhelming at the beginning. WTM absolute value C. And you see this term like this one. So this is what you would expect. You would expect this previous time is where the particle is. This is where the particle is at this previous time, and it influenced the point R in space. You see the C here and the C up here, they will cancel. But this is not all the story, and if it would be, things would be maybe simple, but it's far from all the story. Then you have here R minus W. The W is at time Tm. I'm not going to write it. Times V. Oh. Wow. What an equation. What is V? Okay, this is the potential. This V and that V is not the same. What is V? V is the speed of the particle. It is mind-boggling in the sense that you are educated that at least the usual potential does not depend on the speed of the particle. But here, this is not the case. So what is V? It's, first of all, V at time Tm, and this is W dot. It's a vector. Here I have the dot here. These are vectors at time Tm. So what we see here, if you want, is Coulomb's basic law modified. Usually we are using this part. This is what I call Coulomb's law. This is Coulomb, more or less. It is totally modified in the sense that you have a new term that is much, much harder to explain, but this comes from the definition of the retarded time. Of course, this term depends on velocity. So what happens if the velocity of the particle, we have this particle that is creating the potential. If this velocity is always much smaller than c, very not high speeds, then this term is small, because you see, you need to compare this c with this v. So at high speeds, one second. So at high speeds only does this correction term come in. 1 second, I have the Akshay, so come here. There was a huge delay of 1 hour because I had problems with my computer upstairs. So first of all, they need a break because I'm hammering them. That's one thing. And secondly, I need to finish a few more explanations. So I would say even 1 o'clock. Is that okay? Maybe. You have a seminar at 2. Okay. Okay, so you will start at 12:30. Okay. You usually have 1.5 hours? Okay. So I'll let them know. So if you can tell the people, maybe they only go to Akshay, that you should look at this thing here. So okay, so in Griffiths, you will see a derivation of this equation or an explanation of this equation. He tries to say the following, but he doesn't really explain it. In my opinion, his explanation is very physical and very intuitive, or no, maybe even not intuitive. I mean, it is a hand-waving physicist approach to explain this. What he suggests is to say the following. He notices that in general, this is in general, PR, TR, overall space. What is this object? What are you used to that this object will be? What is this object? You all know, I think.
Q.
Q. The point is, it's not equal Q in our case. Why is it not equal Q? It's not equal Q because in here, sorry, this is R prime. TR depends on R prime. So there is no, this TR is changing for different R prime. There is a different retarded time. This is totally not Q in general. But then he suggests to have some Q effective. He suggests to have some Q effective. This Q effective so, okay, what is Q effective? It's simply rho R prime TR d tau. It's not equal Q, but it is something. And this one is equal to Q, the real charge, 1 minus R minus W hat dot V over C. And again, V, this is all, it's V at time Tm and W at time Tm. So given the velocity of the particle and the position, this is V and M, this hat is a unit vector. So you see this object here is dimensionless. Given this, you can write down the solution for, at least for the potential, as Q effective 1/5 per epsilon r minus WTM. So what he is trying to say, sorry, that we do replace Coulomb's law, but we don't use the Q. We need to use this Q effective. But notice that this is problematic. We need to understand what it does mean, Q effective, because this Q effective itself, in principle, through the V and the W, depends on where you are looking in space. So for each point in space, you have a different Q effective. And for each time in space, you have a different Q effective. He also gives a nice, simple explanation based on Doppler. Why this is true. So what he's trying to say is that somehow what we see is not a usual charge, but a smeared charge. But what I'm going to do, because this is in Griffiths, I'm going to be rigorous. So instead of doing what Griffiths is doing, I am simply going to derive it in the time remaining. This is very mathematical, but I think this is the only way to really understand what's going on through the math, because the intuition here is not so trivial. So this part is not in Griffiths as far as I can see. Maybe, I don't know why Griffiths doesn't give this, but I want to derive it. So again, I have this W of T in principle, and I'm looking for the V, the potential at R at time T. Let us do this. So this is equal to Q, the real Q, 4 pi epsilon, integral over the volume. I'm using here the basic equation. Okay, let me write it down. R minus R prime. We need to write a delta function, R prime minus W, the trajectory, T, minus R prime, C, and I need to multiply by T prime. So what do I have here? I have here the usual 1 over R to the power 1 dependence. And what is this delta function? The delta function is the density, but at what time? At time TR, not TM. This is really TR. I just plugged in here the definition of the retarded time. And you see what I wrote here is a delta function of R prime WTR. And that is multiplied by Q. That is simply rho. And this is the basic rule that we had roughly 1 hour ago in our board. We need to integrate it over all space. I think, is this equation clear? Questions? No questions. Everyone is at the fridge. Okay, let us still continue. How do I solve these type of equations? So the trick to solve these equations is actually to introduce a new integration variable. Here I'm just integration over space. Now I want to integrate over space and time. It sounds like I'm making things more complicated, but eventually this is the way to do this. So I'm going to write this as V, R, and T equal to Q over 4 pi epsilon integral, the first integral over time. That's the new part. The second integral is over d tau. Remember, that is an element in space. 1 over R minus R prime. This is exactly what we had before. Now I'm going to do the following. I'm going to write delta R prime W T prime, and I'm going to multiply this by a delta function of T prime minus t plus r minus r prime. Oh, sorry. First of all, here we have the absolute value, and here I have the absolute value. W, r minus r prime. So what is this thing? This is simply TR, the retarded time. So what I'm doing here, I'm integrating over dt prime, and then all this retarded time will go into this W. That is the trick. Very simple trick in principle. Now, how do I continue? I first integrate over space. And I leave the integration over time for now. Now, why is it easy to integrate over space? Because I have here a delta function. I integrate over r prime. So what do I need to do? Everywhere I see r prime, like here, I just need to plug in the W. So the solution is VRT is Q over 4 pi epsilon integral dt prime delta t prime minus t plus r minus w t prime c. That is again the retarded time. R minus r prime. No, r minus w w t prime and now I need to do this integral. Now it looks simple, but it is not simple at all. Why? Because I have here t prime, but I also have here t prime. And I also, here it's maybe less. If this wt, I would replace it simply by some tm, for example, this integral would be easy, but it's not easy because of t prime and t prime. Then even though it is a delta function, it's not a trivial delta function anymore. So how do you solve this type of integration problems? You define some function u. U is not an energy density, and u is essentially everything that goes here inside. It is t prime minus t plus r minus w t prime c. Why do I do this? Because now I will have a delta of t prime blah, blah, blah will go into delta of u. That is good. But when I do this change of variables, what do I gain? I have an integration over d tau. What will I need to calculate now? It is called the famous Jacobian. I need to have the Jacobian because u is a function of time. If I want to integrate over u, because I'll have in the delta function u, I need to now calculate the Jacobian to do so. So what is u, first of all? U as a function of t prime. Ooh, this is t prime minus t. And now I have all this nice friendly object, which I'm going to write explicitly. Okay, so this is r minus w. So it's x is for r. Then I have minus wx of t prime squared plus y minus the element of w in the y direction, t prime squared plus the z direction. All this divided by c. Now I need to take the derivative with respect to time, because I need to calculate the Jacobian. If I know this, I can switch variables from dt prime to du prime. Oh, this is the following. If I take the derivative of this, this is 1. The derivative of t with respect to t prime is 0. And then I can do this derivative. So I have a derivative of a square root. I have a c in front. So I have this lovely equation. So this is x minus wx t prime squared, again, defined with the trajectory of the particle. I know the trajectory, I know this function. Plus y minus wy t prime squared plus another term with z. And then when I take the derivatives here, I have x minus the internal derivatives. Here I just took the derivative of the square root. It goes downstairs, so a function like x to the power half, when I take the derivative, goes to x to the minus half. This is this part. And now I'm taking the derivative inside. So I need to take internal derivative. The 2 here will cancel the half here. The minus here comes from this minus. This minus gives you this minus. And then I need to take the derivative of wx t prime, derivative with respect to time. And similarly, I'll have y minus w, this is wx, y, wy t prime dt. So now you see that this guy is equal to 1 minus, we can write it in a different way, r. The r comes from this x, from this y, and from this z. R minus omega t prime. You see, x minus wx gives you r minus x minus wx, y minus wy gives you this. It's the same. Let's write it in this way, dot w dot. The w dot comes from this dot and this dot at time t prime divided by r minus w t prime, all this divided by c. Now, I can use the fact that from here, dt prime is du divided by these 3 points. Right? I think everyone can see. I just take this nasty object, I put it now downstairs. That is the point. It now is downstairs. So when I perform the integration, I need to consider u equals 0. Why do I need to consider u equals 0? Because I mentioned before, I have a delta function with respect to u. This was what I had before. So if you want to write it down, what is VR and t? It's the following. It's 1 over 4 pi epsilon 0, as usual. Integral over du now. I change variables of a delta function of u, which is lovely because I know how to do integrals over delta functions, multiplied by this nice equation, r minus w t prime. No, not t prime. T prime, which is a function of u, which is the retarded time. I'll soon explain this. 1 minus r minus w tu, the retarded time. This comes from the Jacobian, r minus t of u . W dot comes from here. T of U divided by C. Now, because of this delta function, when U is equal to 0, what do we get? This is from the definition of U. See from here. I just take U equals 0 because, again, because of the delta function. And this is nothing but the definition of what we had before, which we call Tm. Right? Because if I put here U equals 0, I get T prime, which is equal to Tm, defined by this equation. Tm, this is just a change of notation, T minus R minus WTM divided by C, QED. So the above expression for V, R of T, is our basic claim. What do I mean by basic claim? I mean, this is what Mr. Griffiths announces in his book and explain it a little bit more. But here I simply derived it by brute force. So I want you guys to have a break and please continue reading chapter 10. And we did not discuss yet the electric fields themselves and magnetic fields, but this will be mentioned maybe only briefly next lesson. If you have questions on that, we will focus mainly on radiation. That will be chapter 11. And then, unfortunately, chapter 12, according to the dean, will not be part of this course, which is a great pity. But, you know, there are bigger things going on in life. I hope that, you know, we will have a peaceful time soon. I hope that you guys talk to each other and help each other. I know that some of you have a bigger problem than others. For example, children at home is very complicated. So if you can help each other, it will be very nice. I'm not talking about people in Miluim, that is a different category altogether. There are also people, let's say, with some more tension or people living in more dangerous places. So if you can form a community and help each other and try to learn together, because what is our goal in this course? There's only one goal, to be better than the Iranian students of physics. I'm not kidding here. They are very clever people over there, and we must be better than them. And what I'm teaching you now is towards the end of the course, which maybe is unfortunate, but I chose it this way. But this is the heart of the course. This is the new things of the course. And as you see, these are not so simple things. So I know that you are under pressure and sometimes you don't sleep well, etc. But I really hope that you can overcome this because you are young and you're still young people, in my opinion. So you can handle changes in life easily, I hope. You know, small children, if you put them in a shelter and it's bombed, they just continue playing. They don't care about anything. And I hope that you have some of that spirit with physics. Maybe physics is not so much fun as playing games, but still, this is what we need to do. And I wish all of you, you know, more peaceful times. And we will meet next week. Thank you very much.
Eli, can I ask a question?
Sure.
Why did you want to calculate Q at the retarded time and not T itself?
So Q, if I go backwards, I did not, you're asking on the previous formula, I believe, this Q effective.
Yes.
Right. First of all, it's not me, it's Griffiths. Let me explain the idea. It's very pedagogical and simple idea. I gave you towards the end a mathematical proof of what is VR on T. You see, this is, oh, I even didn't write it down, but it was at the beginning maybe. This equation. This is the solution, right?
Right.
So this is the truth, the whole truth, and nothing but the truth. And I love this equation. Don't misunderstand me. But at the same time, Mr. Griffith's saying, oh, this is complicated. Let us write it in a simpler way. What is the simpler way, quote unquote, only for your understanding of what is going on? He says, we're going to take this guy, we put it outside here, we divide this term by this term, and we call all the remaining Q effective. This is this equation with this definition of Q effective. Now, you can ask, why is this good? If you were calculating things, there's no difference between the two equations. But what you see here is a structure of a theory where I just identified some Q. Okay, that's all.
Okay, yes.
And Griffiths, because we didn't have time, goes a little bit deeper into this in a beautiful way. He tries to explain why he goes backwards to a simpler problem. He says, let us first calculate not the horrible integral that we had before, but this integral. Why is this easier? Because here we do not divide by 1 over r minus r prime as we do in the potential up here. So it's very wise to start with simple integration, relatively simple, which is not simple at all, over rho, just to see that it's not Q. He makes the problem simpler for pedagogical reasons. And then he finds some Q. This is this Q effective. And then he notices that this Q effective, I can write the complicated equation with this Q effective. Okay?
Okay, thanks.
But if you're asking in an exam, will this be helpful for me to calculate things? Unless Q effective is independent of the trajectory and independent of R, the answer is no. The answer is the rich physics is in the complicated equation. This term, especially, also this term maybe is new for you. There is all the rich term, and especially when V is large compared, not to C, of course, you cannot be C, but of order C, then this term is super important, and the relativistic potential is going to be totally different than the Coulomb potential. Just you can formulate it as a change of the Q effective, and please go to read at Griffiths if you are interested. He uses some trains to explain this Q effective. It's a very nice argument.
Okay, thank you.
Thank you, guys. Keep safe. Goodbye.
אלי,
Yes.
לא, גם שאלה? לא,
כן?
לא הבנתי.
מי שואל?
רועי,
רועי.
לא רואים את זה עכשיו כי אין אף פעם מצלמה. לא הבנתי מתי שאמרת ש-U שווה ל-0 בגלל דלתה U, אז איך הגעת לביטוי באינטגרל שזה רק DU כפול דלתה U? זה לקראת הסוף.
כן. איך הגעתי?
נראה לי עוד למטה. הנה, פה, לשורה השנייה מהסוף. השנייה ש-U שווה ל-0 בגלל שדלתה U, ואז מתחת לזה, איך זה...
קודם כל, כל זה,
זה אותה משוואה.
כן, יש פה דוט, סליחה.
אוקיי, זה מסביר את זה.
למה? אני חושב שאתה מבין מאיפה זה צץ, כי...
כן.
כי זה צץ משני דברים, אחד מזה היה קוביאן, והשני זה הדבר הזה, וסידרתי את זה קצת. אז פה יש לך את היעקוביאן, שאני מחליף את הצדדים שלו, צריך לעבור על זה, אבל...
כן, זהו. פשוט לא הבנתי, לא שמתי לב שזה אותה משוואה, שתי השורות, בגלל זה לא הבנתי. אז זה מובן עכשיו.
כדאי אולי לעבור על זה בתרגיל, על כל השלבים. כדי לקבל את הביטוי הזה, אבל הטריק העיקרי, שאני חושב שתוכל להסתדר אחרי שתעשה את הטריק העיקרי, זה להשתמש בשתי דלתות. זה הטריק
כן,
שאני
כן.
מכיר, אולי יש טריקים אחרים, זה מפשט את זה.
טוב, זה לא הבנתי, תודה.
אין בעד מה לטעות.